Hi Rockridge, this is Mrs. Berger again, and today we'll be talking about bivariate data again, two-variable quantitative data. And this is part 2 of our notes for this unit. This is the last of the notes for our unit. Everything else in this unit is practice. So we start on lesson 2.5 in the book, and we talk about regression lines. And so take a look at the data in there. You can take a look at any of the examples in there. There's great material in the book. The first question I want you to answer is, what is a regression line? And what do we usually use it for? And what do we call that use? So hopefully you've been able to gather from the book that a regression line is a line that describes how a response variable changes as the explanatory variable changes. Okay, that's what a regression line is. Basically the line that says as your input changes, how does your output change? And of course we've seen that as y equal mx plus b in the past. We've got a slope to it and a y-intercept, and that describes the change. Now, we're going to look at a slightly different form in a minute here, but keep those lines in mind. What do we usually use a regression line for? We typically don't use it to summarize the data that we have. We want to use it so that we could predict other values, right? Having the variables that we have in the interval that we already looked at, it's interesting, but the best use of this is to try to predict values outside of the interval. So it's most commonly used to predict values outside the interval of actual data. That prediction is called extrapolation, and I'm sure you've heard that word before. Extrapolation. We're extrapolating the data. Now keep in mind, the further away from the original data you extrapolate, the less we feel good about that extrapolation and that prediction. So extrapolating a little bit outside the original data range is probably good. If we go too far, we might get a little less sure about our results. Now, residual. If you've reviewed the text, hopefully you've come to the conclusion that a residual is the difference between actual value of y, or response variable, and predicted value of y. Or the response variable. This is always, of course, based on the regression line. The regression line helps us predict. So if you want a little formula to remember, residual, if you were asked to calculate a residual, you would take actual value of y minus predicted. That right here, let me change colors a bit here, this is called a hat. So we say y hat. So y, that's actual data, and y hat is predicted data. We always take actual minus predicted, and residual does have a sign. It's either positive or negative. So it matters that you take actual and subtract y hat or y predicted. Okay. Now, the format of a regression line. It is similar to the lines you've seen in the past, with a couple of just slight changes. And I've left you a lot of room here so that you can pull out each individual part and label it. So y hat equals a plus bx. And we're going to label each of these parts to explain what each of these means. Y hat is your predicted value of y, your response variable. A is your y-intercept. That, of course, is when x equals 0. Keep that in mind. When your input is 0, this a value is your y-intercept. Your b, of course, is your slope. Your slope, you need to understand that that has meaning. The slope is the predicted change, or rate of change, predicted change in y for each 1 unit change in x. And when you're interpreting slope, you need to use that wording, okay? If b turns out to be a value of 2, that means the predicted change in y is 2 for each 1 unit change in x. And then of course, x is x, it's always your given value of x. Now notice that in olden days, when you were in algebra, you saw y equal mx plus b. We're slightly different here. Y equals a plus bx. The number in front of the x is still the slope, and the number outside by itself is still your y-intercept. So just because we're not using what you're used to doesn't mean that the values have any different look on the graph. So let's look at exercise 2 for this section. So lesson 2.5, exercise 2. We love the crickets chirping, and I know you're shocked to believe that people study this, but people have actually gone out and counted the number of cricket chirps made by the striped ground cricket, the number of cricket chirps based on what temperature it is outside. And they've fit a line to this data, and that line is shown there as y hat equals negative 0.31 plus 0.212x. And given that regression line equation, we're asked to predict the cricket chirp rate when the temperature is 82 degrees. Now certainly understanding which variable is explanatory and which variable is response is important. You should know that explanatory, or x variable, is temperature, which we're given, and response variable, or y predicted, is going to be chirps per minute. So you've probably already realized that you just need to plug 82 degrees in for x and see what pops out. Now, what I do want you to do is document first. The original equation is given as y hat equals negative 0.31 plus 0.212x. When you explain these in context, I want you to realize that chirps per minute predicted, that's a big hat, because I have a big variable there, but predicted, the hat over top of that, that's actually what y is, and that's much more useful. And x is temperature. So this is a much more useful view of this equation. So chirps per minute predicted is negative 0.31 plus 0.212 times 82 degrees Fahrenheit. And hopefully you have gotten the same number that I have. If you've paused the video and calculated, you've gotten 17.074 chirps per minute. So let's keep on with this theme. Question 6 asks about chirps again. If we have the same equation for the regression line, and we have part A asking us one observation is measured at 16.2 chirps per minute at 83.3 degrees Fahrenheit, calculate the residual. What are we going to need to do for this problem? Pause and think about that. And hopefully you realize that we have 2 steps to this problem. To calculate the residual, you need the actual data point and the predicted data point. We have the actual value of 16.2. That's what they actually measured. They actually observed that. What we need to do is figure out what this regression line had predicted it would be based on an 83.3 degrees Fahrenheit. So let's calculate predicted. Let's predict chirps. At 83.3. So predicted chirps is 17.3496, and if you had rounded, that's fine. And since residual equals actual minus predicted, Let's fill that in. Let's fill that data in here. We were given an actual chirps per minute of 16.2, and we just said the predicted was 17. Let's round this, 17.35. If that's the case, negative 1.15 chirps per minute is the residual. That's the answer to that question. That's what the residual is. So that's part A. Part B for this question asks, interpret this. The wording for the interpretation would be that cricket, that observation, cricket had a chirp rate (1.15 chirps per minute) less than expected, or predicted. You could say predicted as well, based on the regression line. Okay, and I hope you're giggling that we're actually having this serious discussion about chirp rates, crickets and their chirping rate. But that's how you would interpret in context. The cricket had a chirp rate, 1.15 chirps per minute less than expected. Why less? Because it's negative. The residual was negative, based on the regression line. Okay? Let's move to question 14. 14 is a little more exciting. It's about roller coasters. The explanatory variable for this is the height of the roller coaster, or the maximum height of the particular roller coaster. And the response variable is how fast it can go, the top speed of that particular roller coaster. So a bunch of roller coasters were plotted here on this scatter plot, and a regression line was calculated for that data. And the equation of that regression line is y hat equals 28.17 plus 0.2143x. So in context, I would like you to make sure that you understand, in context what that means is the response variable being speed, predicted speed, equals 28.17 plus 0.2143 times the height. Okay, that's the equation we're talking about here. And we're asked, for part A, if we have a roller coaster called the Iron Shark, and that roller coaster has a maximum height of 100 feet and a top speed of 52 miles per hour, we're supposed to calculate the residual and interpret the residual. So a lot of this work is very similar to what we just did for the cricket chirps. To calculate a residual, you need to know the actual and the predicted. We were given the actual speed as 52 miles per hour. We have to use the line of regression that they gave us to calculate what the predicted would have been. So let's do that first. Let's calculate predicted. Plus 0.2143, and that height was 100. So the predicted speed was going to be 49.6 miles per hour. The residual is actual minus predicted, and the actual, we were told, was 52 miles per hour minus the predicted of 49.6 miles per hour. So we've got a residual of 2.4 miles per hour. Now let's interpret that. The interpretation of that is the top speed of the Iron Shark was more than expected. It's actually, if we want to be specific, 2.4 miles per hour more than expected, based on the regression line. Okay, that's the interpretation statement. So that's part A. Let's look at part B for this question. Interpret the slope of the regression line. Now I know we haven't done this before, and I would like to give you a little template. Just like we had a template for interpreting standard deviation back in the last unit, I want to talk about the proper interpretation of slope. So let me give you the interpretation of this slope. As you can see, the slope of this equation is here. It's a positive 0.2143. This is the format of the answer to this question. the predicted, that will always be your first word when interpreting slope, the predicted top speed increases by, now sometimes this will be increases by and sometimes it will be decreases by. Since this is positive, in this particular case, it will be increases by. So the predicted top speed increases by 0.2143 miles per hour for each additional 1 foot of max height. Okay, so for each additional one, in this case it's 1 foot, sometimes it's 1 carb or 1 gram or whatever, but this format here, the underlined parts, are what you're going to see each time. The predicted element, the predicted top speed, increases or decreases, increases by 0.2143 miles per hour in this case, for each additional 1 what? In this case, input is height of 1 foot. For each additional 1 foot of height. Okay? That is a proper interpretation of slope, and you should have that format in your head for quizzes and tests. Let's take a look at part C. Does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. If not, explain why. So you'll see this question a lot as well. What does it mean to have a y-intercept of 28.17? Remember, y-intercept is when x equals 0. Input equals 0. In this scenario, that means the roller coaster height is 0. Wait a second. How can you have a speed when you have a roller coaster height of 0? Does that have meaning in this context? So the answer to that is no. The value of the y-intercept in this particular case does not have meaning. Having a height of 0 or a 0 height roller coaster doesn't really, it's not possible to have a coaster with max height of 0 feet. And so that question can be answered that way. And we will again address interpretation of y-intercept in a case where it does have meaning. But in this particular case, it has no meaning. The y-intercept has no meaning. And to explain that, we can simply say it's not possible to have a coaster with max height of 0. Okay. Alright, we'll be moving to lesson 2.6 now, if you'd like to follow along in your book. We're going to talk about a least squares regression line. We've been dancing around this topic for a while now. It's these red lines that they keep fitting to our data. And we're going to define the least squares regression line specifically here, and then we're going to show you some examples in the calculator. So make sure you have your calculator handy for this so you can watch the button pushes and follow along. So in lesson 2.6 we talk about least square regression line as the following. It's a line that makes the sum of the squared residuals as small as possible. And there's a great graphic in the book that helps explain this. This graphic is on page 138 of your book, or if you're on the online version, it's near the beginning of lesson 2.6. And it's a great explanation of the difference between or explaining what a residual is and what a least squares regression line is. So what your calculator is doing, and we'll never ask you to do this by hand, but what your calculator is doing is it's taking each of these points, each of these data points, and trying to make a line that goes through the data points so that each of these little distances here, or residuals, so each of these lengths of these lines is residuals. And we knew that, right? Actual minus predicted, actual minus predicted, actual minus predicted. It's trying to draw a line. It's testing and testing each time it tries to draw the line. It's drawing the line for which each of these little distances, these little residuals, are as small as possible. And since residuals can be negative, it makes sure that the squares of the residuals, it positizes them basically, it makes sure that the squares of the residuals is as small a number as possible, and it doesn't stop until it finds the line that goes through the data points or goes between the data points that makes those residuals, the squared residuals, as small as possible. So that's why we call it the least squares regression line. We keep the squares of the residuals as small as possible. So now let's take a look at the least squares regression line. On our calculator. Now, we're going to put some data in here for a particular problem, but I just want to walk you through the steps for actually calculating a least squares regression line. I believe you've done this in the past already, but let's refresh our memories. Of course, we want to start by entering data. So we hit the button Stat, Edit, and we put data into List 1 and List 2. Once we enter that data, we need to calculate a least squares regression line. And absolutely, if you want to take a moment to look at your data, certainly do a zoom 9 and take a look at your data. But to calculate a least squares regression line, you go Stat, Calc, and in the past you may have used choice 4 for a linear regression, AX plus B or MX plus B. We're statistics students now, and we want to use choice 8, linear regression, in the A plus BX format. So use choice 8. And of course our data is in fact in list 1 and list 2. And we'll calculate our least squares regression line. Remember the format of this, your calculator is telling you y hat equals 13.9 plus, or actually minus, 0.28x. That's what your calculator is telling you with this. Okay? So just to refresh our memories and to take notes on the steps we just took, we Stat, Edit, enter data in list 1 and list 2, and then we Stat, Calc, linear regression of the format A plus BX, and that's choice 8. We'll remind ourselves later, but certainly using the mode button and turning stat diagnostics on will give us some great values that we probably remember from Algebra 2. So we'll be reminded of that. If you want to do that at this point, you can do it now. Turn it on. Alright, so we stat calculated a line, and I'm sure you're surprised that that data that I looked at was actually for a lesson in the book that we're going to look at now. So the lesson in the book that we'll look at now is exercise 14. And this lesson, or this example rather, takes a look at beans. I know you were really excited about the build-up for that, right? I was scrolling to a problem about beans. So the data that we have here measures the carbohydrates versus protein of various beans and other legumes. And so what we're asked to do first is to make a scatter plot to show the relationship between protein and carbohydrates. So we want to put carbohydrates in our list 1 and protein in our list 2 so that the explanatory variable is carbs and the response is protein. And that of course is the data that you saw in my calculator. I want you to take a moment to pause the video and enter this data so that you can follow along with me. Enter that data into list 1 and list 2. Pause if you need to. Take the data out of the book and enter it into the calculator. Alright, hopefully you've had a moment. You paused the video to enter that data. We are asked to plot the data, so of course zoom 9 to see it. And we can capture that in a hand-drawn scatter plot. What we saw was basically a data point here and some data points here, right? And we're asked to calculate the least squares regression line. Using technology, calculate the equation of the least squares regression line with y equals protein and x equals carbs. So, hopefully you've already done it with ahead of me, but that's stat, calc, linear regression, And since I've turned stat diagnostics on, I get my correlation and my R-squared, which I'll talk about in a little bit. But what we need to see here is this equation here being filled in with this for an A, this 13 for an A, and this negative 0.28 for the B. And we'll capture that as an answer to our question as follows. Y hat equals 13.9 minus 0.281x. Now let's remind ourselves what that means in context. Our response variable is protein. So we're basically saying predicted value of protein equals 13.9 minus 0.281 times the carb value. Okay, that's in context. Now, let's take a look at question C. What effect do you think the observation for soybeans has on the equation of the least squares regression line? Calculate the equation without this variety to confirm your answer. So soybeans, hopefully you saw in the data that the soybean was right there. When we had that on our calculator, the soybean is this point up here. And if we were to take that point out, we need to understand what would happen. So right now, the line of best fit has a negative slope. Remember that? Negative 0.281. So the line of best fit goes through here. But imagine if we took this soybean data point out and just had this data down here, we would have a positive slope regression line, wouldn't we? Look at what that soybean does. The soybean drags the regression line negative. And I want you to take a moment and remove that data point. I believe it's the first data point on your list. Go in your calculator and remove that data point. Simply go to the soybean data point, which is the top one, and clear that value. Oh, maybe it's delete. Sorry. Delete that value. Come on. And delete its corresponding value. And you're just left with the 22.5 and the 7.0 at the top of the list. So now we've taken the soybean data out. Now let's look at our data again. And let's calculate the regression line now that that data point is gone. Take a look at that. Now that B, that slope, is positive. So to answer this question, with soybeans removed, our new regression line is protein equals 4.77 plus 0.13 times carbs. Okay? It moved it to a positive slope. Okay, I'm going to move a little faster on question 18. I'm going to assume that you pause the video and enter data for yourself. We're moving to question 18 on the next page, talking about fuel efficiency. And I want you to take that data in question 18 and enter that data into your calculator. Pause the video to enter this data into your calculator. Speed of the car versus the fuel efficiency of the car. And enter that data into list 1 and list 2. And fit a regression line to it. Pause the video and go ahead and do that. Once you're finished, let's sketch that let's document the line of best fit. So hopefully you saw a line of best fit of y hat equals 29.9 minus 0.00593x, which interpreted means the predicted mean fuel efficiency decreases by y decreases when we're interpreting the slope for part A. For part A, we're asked to interpret the slope. We start off with the word predicted always. Predicted mean fuel efficiency, that's what y hat is, mean fuel efficiency, decreases by, why do we say decreases and not increases? Because of the negative sign, okay? So the predicted mean fuel efficiency decreases by 0.00593 miles per gallon for each additional one, that's always in your slope statement, for each additional 1 mile per hour of speed. Okay? Part B. If you calculated this regression line without actually looking at the data, go ahead and zoom 9 on that data right now, and let's sketch that scatter plot. Pause if you need to. But you should see a scatter plot that kind of looks like this. I know it's not perfect, but it kind of looks like this. And we're asked if this least squares regression line that we've calculated here is appropriate for part B. So we used it. What does the slope of the line suggest? We just interpreted that. Now we've made a scatter plot, and we need to draw a conclusion about the applicability of the least squares regression line. Hopefully you see that this is not linear. This is a non-linear relationship. And so we need to declare that the least squares regression line, after we did all that work, is actually not appropriate. It's not appropriate. The relationship is not linear. So again, just like with correlation, least squares regression line, you can certainly analyze all you'd like from the numbers, but if it's not a good model based on what the data looks like, it was all for nothing. So make sure that you do look at the data each time you calculate the model. Alright, we're going to wrap up with lesson 2.7 for this unit. Lesson 2.7 talks about scatter plots and residual plots, and we need to do a compare and contrast on these. A scatter plot, you already know, is your actual data plotted. And it is x with respect to y. Very simply, scatter plots are the actual data plotted. Residual plots actually are the residuals plotted instead of the y. Okay, the residuals are plotted. It's x with respect to residual. There's a great picture of this in the book. Page 149 shows this amazing example of a residual plot. On the left is a scatter plot. These points are a scatter plot of the Super Bowl 0 through 45. Obviously there wasn't a 0, but the Super Bowl 1 through 45, and how much the cost of a 30-second commercial was. So you see the cost of the commercials were going up as the Super Bowl numbers go up as far as the scatter plot is concerned. And of course a line of best fit might look like this. On the part B graph, we don't have a scatter plot anymore, we have a residual plot. Our x-axis is still the same, Super Bowl numbers 1 through 45, but instead of the cost of the commercial on the left, we have the residual. So each of these blue dots is actually actual minus predicted. Actual minus predicted. Actual minus predicted. Actual minus predicted. If you can imagine lines drawn and calculated between the point and the line, the height of that line is the residual. So the height of the line between the blue dot and the red for Super Bowl number 1 appears to be about maybe $650,000. Okay, that's the residual. And the residuals should hover around 0. Some of them will be above 0, some will be below 0, right? Because we have positive and negative residuals. Some of the predictions were high and some of the predictions were low. You will need to plot a residual plot for your lab, so make sure you're comfortable with understanding how to do a residual plot. Certainly not for 45 data points like this. It's going to be much fewer. It's more like 8 or 10. But you need to calculate actual versus predicted so that you can create a residual plot for your lab. So that's the difference between a scatter plot and a residual plot. Now, how do you determine, based on the residual plot, how do you determine if a regression model is appropriate? So this is a really neat trick. Certainly from a residual plot perspective, most residuals should lie along the horizontal line of 0. Okay, that's true. Also true, residual plots should show no pattern. If you see a pattern, the least squares regression line is not a good model. Okay. We should try to keep these residuals as small as possible, obviously. Otherwise the line is not that great a fit. Let's compare and contrast two different, our last two pieces of variable here, correlation coefficient, which we've talked about before, and coefficient of determination. Both of these things are things that your calculator will tell you about as you calculate these lines of best fit. So from the book or from your previous experience or even just from earlier lessons, we're going to compare these. Correlation coefficient, as a reminder, is strength and direction of a linear relationship. And it's always between two quantitative variables. Coefficient of determination is slightly different. Even though it's r squared, it's slightly different. This measures the variability, well, let me be more specific, the percent variability in the response variable that is associated, or that is accounted for by the least squares regression line. So basically we're saying if your calculator spits out an r squared, this is for the soybean example, an r squared, once we took the soybean out, it said the line of best fit had a 0.396% variability accounted for it. That's not a lot, okay? The r squared variable is going to be between 0 and 1, and a 0.396 is pretty low. So this is basically saying not a whole lot of the variability is accounted for by this model. It's not a great one, okay? So r squared is a value between 1 and 0. And this is basically saying how well the regression line makes predictions. These are different items. Even though they pop out in the same window on your calculator, be sure that you know what each of one of them means in context. Okay? And again, to make sure that r squared pops up, you need to, this is typed into your notes, you need to turn stat diagnostics on. That's what this note is right here. Make sure that stat diagnostics is turned on in the mode menu to view r squared, the coefficient of determination. Alright, let's look at our last few examples here. So in section 2.7, we're looking at exercise 4 first. This exercise talks about, does the grill stay hot? So basically, statistics teacher turned off their grill and timed and took information or took data as time went on about how the temperature dropped after he turned off the grill. What you're looking at here is not a scatter plot, it is a residual plot. And so you will be asked to interpret or to determine whether the regression model is appropriate. So remember, he drew up his scatter plot, he fit a line to the data, the line of best fit, probably using his calculator, and then he took that line of best fit and took each of those original pieces of data and took the actual minus the predicted by the line and plotted those residuals right here on this. And we're asked, based on this residual plot, Is the regression model appropriate? Hopefully you see a pattern. We see it come down and then go back up. It's a curved relationship, and we have quite a few data points below. It's a U-shaped curve. We don't like patterns in residual plots. So we will declare for question 4 that the least squares regression line is not an appropriate model because there's a U-shaped curve in the residual plot. We would much rather have seen data points above, hovering across this 0. We hate this 60 so far away from the 0. It's a horrible residual. It's too far. We would much rather see the data hover around this 0 with no particular pattern to it. Okay? Alright, let's move to question 18. Question 18 takes a look at some data based on the number of minutes and the number of floors climbed on the stair climber. Okay? We record the minutes of climbing time and the number of floors climbed for 6 different exercise sessions. So 15 minutes she climbed 73 floors, 16 minutes she climbed 82 floors, and so on and so forth. And so we're asked to sketch a scatter plot for this data and calculate the equation of the least squares regression line using technology. I want you to pause the video right now and enter this data into your calculator and calculate the line of best fit and then check it against mine. Go ahead and do that now. Alright, hopefully you've had time and you came up with the following. For a sketch of the scatter plot, hopefully you saw something that looked a little bit like this. And you have minutes on this axis and floors on this axis. And you saw a line of best fit that looked like this. Y hat equals negative 3.822 plus 5.215x. If you did not get that, please go back and try and make sure all of your data was entered properly. This is definitely something that goes wrong on quizzes and tests. Be very careful about data entry. Now, if we were to interpret what this means in real life, predicted floors equals negative 3.822 plus 5.215 times the minutes. Okay. Now, for B, you will need to construct a residual plot. Now remember, for each of these data points, and it's only 6 data points, so you're going to take each of these data points, we've got an actual value, and now, based on this equation, we can calculate a predicted value. So you will need to calculate predicted values for each, for each of these data points, predicted. So what is the predicted value at 15 minutes, the predicted value at 16, at 18, at 20, at 22, and 25. You'll need to come up with Y hats for each of these. And then you'll need to take the actuals, 73, and subtract your predicted. Actual of 82 and subtract your predicted. Actual of 88 and subtract your predicted. And plot those residuals on the residual plot. Please pause the video now and construct that or sketch that residual plot. Alright, hopefully you've had time to do that now. And your residual plot should look like this. Oh, I probably should, well, let me put 0 here. So there's 0. And your residual plot should look kind of like this. Maybe not perfect, but kind of like this. If this is minutes, this is floors. Oh, sorry, this is residuals, right? It's no longer the Y. This is residuals. Okay, and you have a couple of positive residual, you have 3 positives and 3 negatives. And so we love this residual plot, right? There's no pattern to the data. The LSRL is an appropriate model because we see some below, some above. It's hovering close to 0. There's no leftover pattern. There's no pattern to the residuals, and so we love this residual plot saying that the least squares regression line is a great model. Now, I did not ask you to do part C, I wanted you to do part D. When you ran your LSRL, you should have had an R squared. So go back and grab that R squared. Take a look at that. If you need to pause, go ahead and grab that. And hopefully you saw an R squared of 0.989. And question, oh, not C, part D, sorry. Part D, calculate and interpret the value of R squared. We want to interpret this. So again, this is part D. We want to interpret this. This is the phrasing I want you to use when interpreting these R squareds. 98.9% of the variability in the number of floors is accounted for by the model, by the LSRL. With x equal to time working out. Okay, so the underline is your little template that you'll fill in each time. So you'll interpret R squared with that sentence. 98.9% of the variability in the something, in the number of floors, for this particular case, is accounted for by the least squares regression line, with my input variable, or my x, as time working out. Alright, that is the last thing we needed to learn. You can now finish out your homework and let us know if you have questions.